This video is about differentiation by rule. So in our last video, we looked at linear functions and how the slope of the linear function was the same as dy dx. So here we have our linear function y equals 2 over 3x plus 2. Notice that it's 2 over 3 because the rise over run is 2 over 3, that's our slope. And it's 2 because that's where it goes through the y-axis, that's the y-intercept. In that case, dy dx is the same as the slope, which is 2 over 3. And of course, with the line, the slope always stays the same. So there's no worry about any kind of variation within that dy dx. It's never going to change. It'll just be one value, a constant. And in the case of a linear function, it's easy to pick out the derivative dy dx because it's just the coefficient of the x. Now, let's consider the case of a quadratic function. So a quadratic function is decreasing in some regions and increasing in other regions. So obviously its slope is changing, which means that its derivative depends on where on the curve you are. This particular quadratic has an equation y equals x squared minus 4x plus 4. I can't just use rise over run to identify what the slope of the quadratic function would be because it keeps changing depending where I am. Here it's sloping down, for example, and here it's sloping up. And as I can also see, the quadratic function is more complicated than the linear function, so I can't just pick out the coefficient of the x term to identify the derivative. Instead, I have to use differentiation by rule. There's three things to be aware of in differentiation by rule. First of all is that if I have a power on a variable, I will bring that in front of the variable and multiply, and I will reduce my power by 1. In this case, that gives me 2x to the power of 1. The next thing to consider is what happens if I have just an x term. Well, if I have a term that ends in just x, then I'll drop the x and keep the coefficient. So in this case, that's just minus 4. And if I have a constant at the end of the function, I'll just eliminate that when I'm differentiating, so that disappears. So in this case, dy dx is just 2x minus 4. You can see in my derivative here that I've got an x in the expression still. And that's useful because that allows me to work out the slope of the quadratic in different locations on the quadratic. You'll see here in the diagram that I've just marked in the point 1, 1. So the point 1, 1 is on that quadratic. So I could use my derivative now to work out the slope at 1, 1. Notice that the point 1, 1 is made up of an x and a y part. If I substitute the x part of the point into dy dx, into the derivative, it will tell me the slope. So I'm taking 2x minus 4 and I'm filling this 1 in for the x. When I evaluate it, I get minus 2, which tells me that at this point, the slope of the quadratic is minus 2, and you can in fact see that the quadratic is sloping down at this point. You'll see that I've marked in now on my quadratic 0.44. 0.44 is also on this quadratic. And I'm asking the question, what is the slope at 4,4? So again, if I'm being asked for slope, that's really asking me for the derivative. So I want to find dy dx. I know that my 0.44 is made up of an x part and a y part. And if I sub that x value into dy dx, in here for x, it'll tell me the slope at that point. And in this case, I get an answer of 8, which means that at this point on the quadratic is sloping up with the value of 8. And we can see quite clearly in the diagram that it is increasing, that it is sloping up at this point. Okay, so let's just scale this back a little bit and practice some differentiation by rule. So here's my first example. Y is equal to 3x squared plus 5x plus 1. I want to find dy dx. So first of all, I look at the 3x squared term. I'm going to take the power, I'm going to bring it in front and multiply, and I'm going to reduce my power by 1. So when that 2 comes down and multiplies by the 3, it's going to give me 6, and my power reduces down to 1. The x term, I'll drop the x and just keep the coefficient of the x. The 1, the constant, I drop completely. I can tidy up a little bit because that power of 1 isn't strictly necessary to say 6x plus 5. So here's a second example. I've got y this time equals 7x cubed minus 4x squared minus 3x plus 2. And again, I want to find dy dx. So first of all, I've got 7x cubed. So again, that power is going to come down in front and multiply by the coefficient. And I'm going to have 21x squared. So notice not only did the 3 multiply by the 7, but I also reduced my power by 1. In my next term, the 2 needs to come down and multiply by the 4. And that's going to give me minus 8x. You can write the little 1 in here if you like, but you don't have to. Next, I have my x term, minus 3x. In this case, I keep the coefficient and I drop the x. And finally, I have the constant term, the plus 2, which just gets dropped. And here we have an example. Y equals 7 minus 5x plus 6x squared minus 1/3 x cubed. And I want to find dy dx. Okay, so this time my first term is the constant, so it's going to get dropped. I'm straight on to the x term, where I keep the coefficient. Jesus, the window. Next, I've got to bring the 2 down and multiply it by the coefficient, which is going to give me plus 12x. And I can drop the power by 1. And again, that 1 is optional. You can write it in or you can leave it out. And then finally, that 3 is going to come down and multiply by the minus 1/3. That's going to give me minus 1 and drop the power by 1. So I've got squared. At this point, you should go to your book on page 516 and complete question 1 to 21.